Alright, what's going on, everyone? I think I'm recording. Yep, mic's working. Hello, hello. Cool, last time I started recording, my mic wasn't working, so that sucked. Today's video, I think I'm gonna finish up, we're gonna start binary trees, I believe. Yep, binary trees. I don't know how much of binary trees I'm gonna go through. We will see. We will see. I'm gonna try to learn binary trees. Let me see Nicode's. Where is Nicode? Nicode. Let me share my screen. Oh, it does have binary search. Is that what we're learning? Binary trees, not binary search. Trees is right there. Anyways, let's get started. By the way, we hit 100 subscribers, so I appreciate anybody to support. I've been checking the comments. Some people are saying, I seen somebody say right here, that yeah, LeetCode's not gonna help you get a job and stuff, but yeah, I know that. I'm just not on YouTube. I'm doing my own stuff, like building projects on my own. Yeah, trying to do I'm trying to learn TypeScript and stuff, but it's kind of hard because I don't have prior knowledge, so it's taking me a while. I'm trying to finish my personal portfolio. When I finish it, I can share it to you guys. I'm gonna be working on it after this. It's just that when I get on my PC, I don't really, I can't. When I record a YouTube video, I could do it on my laptop. It's just I have all this set up and stuff. So on here, I usually just do my LeetCode. Try to learn more on LeetCode and then upload it. Hopefully, maybe, I don't know. My goal is by the end of July to be LeetCode ready, solve problems, and understand most of the concepts. But yeah, it's kind of hard because there's a lot. So I'm just trying to get better, and then build projects on my own and network and stuff. So yeah, I appreciate the comment though, non-linear ninja. Yeah, I'm maybe in these videos I can start doing projects on here, because I don't know if you guys know my setup. I have a PC here with the screen, all that type of good stuff. So when I record, I have this right there, but all my stuff is right here. When I learn, it's on my ThinkPad. When I build stuff, it's usually on my ThinkPad. So yeah, hopefully when I finish this data structures course, we can move on to some other stuff in Python, and probably build projects here on that. And I need to go back anyways and learn some other stuff. So yeah, sorry for all the yapping. We could get straight into it. So we finished linked lists. I understand linked lists to an extent. I still need to get better at it, but yeah, my goal is just to learn as much as possible and then go try to solve problems and have a clear understanding, like a prior understanding of what I should like use, and then learn the problem. Not memorize, but understand what to do. So alright, let's get straight to it. So trees. Trees are widely used data structures that simulate a I can't even say that word. Dude, oh my god.
Hierarchical.
Hierarchical. Yes, heard that.
Hierarchical.
Hierarchical. Oh well, tree structure. They said that they're typically drawn upside down. The root node is on top and the leaves are in the bottom. The root node is on top and the leaves are in the bottom. Trees are kind of like linked lists in the same sense that the root node simply holds references to the child nodes, which in turn hold references to their children. But tree nodes can have multiple children instead of just one. A generic tree structure has the following rules. Each node has a value and may have a list of children. Children can have a single parent. Right, that would make sense, yeah. Yeah. Yeah, okay, I see. So linked list is node, 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 right? Tree, draw from left to right in this case, is node, node. Okay. Multiple nodes in a tree can have the same value. Multiple nodes. Well, 2 is right there. Yeah. Parent nodes have blank children. It can have multiple children. And children can only have one parent. I understood that right away. Alright, let's watch this video. CA. I gotta be careful because my mic is hella loud.
Unbeknownst to our programmer.
Hold up. Before I watch this video, binary trees aren't particularly useful data structure unless they're ordered in some way. One of the most common types of ordered tree is a binary search tree, or BST. A BST has some additional constraints. Just kind of curious. Binary search. BST. Binary search. Oh, okay, I see. Okay, let's just exit on my video. Come here. Binary search tree always has some additional constraints. Instead of an unbounded list of children, each node has at most 2 children. Instead of unbounded list of children, each node has at most 2 children. Okay. The left child's value must be less than its parent's value. The right child must be greater than the parent's value. No 2 nodes in BST can have the same values. By ordering the tree like this, we're able to add, remove, find, and update nodes much more quickly. Dang, so the left side child's values must be less than the parents, and then the right side must be greater than the parents, and then no 2 nodes must be the same.
Humor. Binary trees are actually used in the real world, not just as fodder in LeetCode style interviews. Binary trees are the quintessential data structure. They're the ultimate tool for efficiently storing and organizing data. Unlike stacks or queues, a binary tree can be searched for a specific item and can be searched quickly. Binary trees are made up of nodes where each node contains a value and references to at most 2 other nodes, which is what makes it a binary tree. Those 2 nodes are called the left and the right children. The top node is the root, and the tree grows down from the root. So what makes binary trees fast? Well, it's that they are always pre-sorted. Every node to the left of a parent node has values less than the parent, and every node to the right has a greater value. Sometimes a binary tree just stores numbers, which makes greater than and less than operations really simple, but usually they store more complex data like employee information. When they do, we just need to pick an ID, which is just a number, to sort by instead. This less than, greater than structure is what gives binary trees their fast searching capabilities. Let's say you're looking for the number 6 in a tree. You start at the root and move down, and at each node, you decide whether to go left or right by comparing 6 to that node's value. Each time you make a comparison, you're eliminating half of the tree. We don't have to compare against every node in the tree, just one node in each level of the tree. This process is called binary search, and it means that even in the worst case, the number of comparisons is limited to the height of the tree. In big O terms, that means that it takes order log n time to search the tree instead of order n, or linear time. If there are 1 million items to search, and each comparison takes 1 second, then a linear, or order n, brute force search takes almost 12 days. With a binary search tree, it takes about 20 seconds. But it's not just the searching operation that's fast. Inserting, updating, and deleting are all order log n as well. That's why binary trees power databases, file systems, and even Google searches. While you don't get those sexy order 1 operations that you would get with a stack or a queue, at least you can search the thing, some things that stacks and queues don't allow.
That was a good video. I understand what it is. It's just pretty helpful. Pretty helpful. Nodes in a binary tree can have at most. Nodes in a binary tree can have at most blank 2. Binary search trees as opposed to generic trees must be unordered, randomized. Yeah, ask me one of these. So. Wait, what? Binary search trees. Okay, let me turn up my volume because I don't know. Okay. Binary search trees as opposed to generic trees. Binary search trees as opposed to generic trees. Okay, trees. Okay, so binary search trees. What we know is that the left side, it has to be greater than. So order left child, right child, parent. Left child, parent, right child. How would that work? Okay, these two know. I feel like left child, parent, right child. Yeah, this one makes the most sense to me. Shit. Now we into assignment. So, insert nodes. The building block of a BST are nodes. In our implementation, we will only use a single class BST node. So BST class. Any BST node is technically also a full binary search tree with itself as the root node. It's not aware of any potential parents. All our methods that traverse the tree will do so recursively. Have fun. All our methods that traverse the tree will do so recursively. Our locked in BST node. Throughout this chapter, we'll be building a binary search tree to power locked in's custom database. Throughout the chapter, we'll be building a binary search tree. Locked in management doesn't trust so-called open source, so here we are. One of the primary features of database is the ability to look up records by a single key. Advisors are the most common way to look up. Each node in our BST represents a login. A BST has three properties. Value. The value of the node, a user object in our case. You'll notice a user has a name and ID. Name and then ID. Right? Comparison operators are often implemented for your class, so you should be able to compare user objects with equal, less than, or greater than directly. The ID is the value that we'll use to determine the order of the node. The left child of a node, another node, or none. The right child is another node. So assignment, complete the insert method. Okay. Insert method of the BST class. It takes a value as user. It takes a value as user class as input and adds it to a new node. It takes a value as user class as input and adds it to a new node if the value doesn't already exist in the tree. So if okay. What is it? Do I have a pencil? Yeah, I do. Okay, we'll just use I can't even have lane out of this, huh? Alright. So complete the insert method of the BST node class. It takes a value user class as input and adds it to a new node if the value doesn't exist in the tree. If the node doesn't have a value yet, just use the given value and be done. I like to use GPT so it breaks it down. What is a BST node? This is a class that represents a single node. Here's what it stores. Self.val. So self.val, this is the user or the node. Self.left, this points to another BST node that is less than the user smiley. Okay. The insert.val method. This method takes in val. This method takes in a value, which is a user object. You're inserting this value. So you are inserting this value into BST following the standard BST rules. The logic you need to implement. I don't want to look at this. Visualization idea. Try drawing this out. Example, if you insert users with these IDs 5, 3, 7, 1, 4, you choose 5. Oh. So 5 is the head, it's the first node, the parent. And then it goes, 3 goes down there, 1 goes there. 3 goes there, 7 goes to the right, 1 goes to there. Ah, fuck, I get it. Each time you insert, it compares IDs and moves left to right accordingly. I see, got it. See, this visualization idea is all I need. This is the problem with this program. They have no visualization. Like, it doesn't show you visually like what it's supposed to look like, and when I see it, I get it. Like, okay, so I get it. So complete the insert method of the BST node. It takes a value as user class as input and adds it to a new node if the value doesn't exist in the tree. So first step, if the node doesn't have a value, so if I do so one, if sorry if you guys hear the people cutting grass outside, I'm sorry. Oh shit. So if the node doesn't have a value yet, just use the given value and be done. So if node doesn't have a value yet, dang man. Sorry if you guys hear that outside, I know it's annoying. So if self.val, so if the value takes a user class. I'm kind of confused. Shit. self.val. Yeah, see, this is the user object stored in the node. Okay, so if self.val, so if it doesn't have a value, so if the self.val has none, if it's none, just use the given value and be done. Self.val equals val. If self.val is equal to val, so if no, this smells like fucking gross. If the node value is equal to the given value, just be done. No duplicates allowed. Break? Fuck. I don't know. Be done. If the given value is less than the node's value, if self.val is less than the next one, so I go dot next. If something is less than self.val. I'm kind of lost. This is what I have so far. Oh, what you got right? Checking if the node is empty. Just return, like, just re. So we got a few things to break. Okay, so the first one's right? Checking the node is empty. Self.val is none. Yes, there's an initialized tree. Checking the duplicates. So also great. Oh wait, what? Hey, that's right. Okay. So using break. So that was the issue. So 2. The condition self.val next less than. No, the condition isn't quite right. You're comparing the node's own value with something called .next, which doesn't exist in a tree node. You're not working with linked lists. There's no .next. Oh, okay. Sorry. VST. What should you be comparing instead? Think you're inserting a new val. What should val be compared to? Less than the value. If the given value is less than the node's value. Oh, all the way around. So this is self.val. So if the given value is less than the value and the node, wait, if the given value is less than the node's value and node doesn't have a left child and self.left is none. Alright, is none. Create a new left child node with the given value. So that means that self.val, so self.val dot left. I think this should be dot val dot left, right? Is equal to the value. That's what I'm guessing. You're checking the notice that if self.val is minor issues. Checking the values lesson is good conditional thinking. So accessing the left from self-develop instead of self. If val problem. Self.val is a user object. It doesn't have a left or a right. Tree structure. Oh fuck, so it is that val. Ah shit. Okay. Five has the val. I don't fucking know. Has to exist. The logic felt right. It has to equal the value. Right now, all your if statements will run, even if the first one succeeds. That could cause multiple branches. Yeah. Yeah. That makes sense. Right, that's an issue solved. So, wrong comparison. If VAS is less than self dot left. No, we want the self dot left. If that one's less. Yeah, that makes sense. Wait, what? Self dot left. No, we make self dot left equal to value. This has to be right. Again, sorry for people mowing the lawn back. Dang! Of course they want to mow some grass when I'm recording a video. This condition is broken. Self dot left. Wait, what? No. This would be value. That's what? Self dot left is less than value. Self dot left is a BST node, not a user object, and you're trying to compare it directly to value, which is user. What you probably meant was comparing self dot value that tells you whether to go left or right. Self dot left, this part is good. It checks if the space on the left for self is value less than self dot value. That tells you the insert on the left side. The value is less than. I'm not okay. Example of the truth. Let's say self dot value is user with ID. See, I need this. Okay, it's a user with ID 10, and you're inserting a value. A user with ID 7. If 7. Oh, so self dot value shows that it's the node. Oh, okay. So then we're gonna make self dot value less than value. Then we're gonna make self dot left equal the value. Self dot left is empty, so that's gonna be. Should we make this equal to the self dot value then? Right? That makes sense. And it's not the value. Let's break it down. Wait, let me see this. If self dot value's ID here is equal to 10, and you're inserting a value, a user with ID 7 is less than 10, so it goes left. So if it's empty, insert it over here. If not, call insert. Oh, we have to insert that motherfucker. So self dot left dot insert the value. Well, self dot val. I didn't mean to run it. Holy shit, my stomach hurts. My stomach hurts. If I need to go left and left is empty, insert into the left. But think about this. You just said self.left is none. So if self.left is none, how can you call? You can't call insert on none. It'll raise an error. Oh, I thought you can insert it into none. Right? Ask yourself, if self.left is none, if self.left is none, what should you create before trying to insert into? You should be assigning a BST node, like I'm gonna create a new. We want to create a new node. We're creating a new node, then we want to put. Boom, now we made a left one. And now we want to put self.val. We need to insert the 10. Sorry, the left side is lower. Where was the example here? I think it was area 7. So let's say self.val is a user with ID 10, and you're inserting val. You use 7, so go left. If insert a new node there, if not, call insert on the left child recursively. So if the left is empty, now we call self.left. Now we want to insert the new node there. We want to insert the new node there. The new node would be val, right? We want to insert that new node val. Oh, fucking just tell me. Val is a user object, but self.left needs to point to a BST node. How do you point to a BST fucking node? So do I put self dot left dot val? I'm not getting the BST node and the ID stuff. What is a val? Val is a user object. That means it has an ID. So value is a user object. That means it has an ID and a name based on user class. Don't worry, the comparison operator is less than equal behind the scenes. So this is valid. So if val is less than self.val, because user has a custom way of comparing based on ID. What is self.left and self.right? These are to point to other BST nodes, not values, not users. So BST node. So self.val is a user object like Alice. BST is a BST node. Self.val is the user inside the left node. So yeah, it's not that. Yeah, we're not trying to get. So you replace the entire left node with the user that's already inside. There's no way. You should be asking, is self.load empty? If so, create a new node there using the val user. You forgot to use. So if there's no left node, right? There's no left node. We create a new one there. Oh, we just say BST node val? Are you serious? we literally say BST node. This, there's no way that works. Something that equals this. Okay, explain to me how the works. So, yeah, okay. This class defines a node in a binary search tree. Each node has a value and a user object, a left child and a right child. When you create a new BST node, it starts off with no children, left and right are none. Stores the current value, a user object like user. Stores the current value. So starts off with no children, left and right are none, right. Stores the given value, a user object like in self.val. For example, node equals BST node user 101. This at this point node.val ID is 101. Node.left is none. Now let's go over it. Insert one. Def insert one. This function adds a new value and a user into BST in the correct position. Step by step. If self.val is none, this checks if the node has no value yet. If so, we store the incoming value as usual, and then we're done. That one node.bst node says node.value is none. We assign one to duplicate value. So self.val is equal to val. Return self.val. If the val already exists in the tree, we're comparing users by their ID. We do nothing and return early. This prevents duplicates. Greater value inserting left. If self.val is less than the val and self.left is none, it was the BST node value. This checks is the new value greater than the current node's value, and is there no left child? Wait, this is actually backwards. This is like if new value is greater. Dickhead, that's what I did in the beginning, no? I swear I did that. If I didn't, rewind the clip and send it to me, bro. I swear I did self.val. If the val is less than the self.val, because it stores the value and then checks if the next value, then it's none. If value is less than self and left is empty, insert left. Also, if left and right already says use your recursive, so yeah, so that's what I was saying. So if dot left is not none, we're gonna do self. We're gonna recursive, so we're gonna insert. So self dot left dot insert insert the val. I'm gonna do this right side on my own, because I think you're only handling values less than self that way. Oh, well, yeah. Okay, shut the fuck up. I'm doing something wrong. So, so if if the self dot value is less than, sorry, what the heck, less than the value, and the self dot right is none. Same logic goes before. We make the self dot right equal to the BST node, and then we enter the value, and now we do what else? Curious. Else self dot right dot insert val. Wait, I mean that. And at the end I return shit. So these are probably going to this right side. So if I put elif the self dot right side is not none, right? That would make sense, right? Make sure this is indented, right? None, I meant none is not none. Still fail, fuck. Dickhead is wrong. Since we already checked if the given value, so should be less than. So 765 into the trees. 765 pass expenditure. 14, 13, 10, 6, 10. So 14, 10. So this should be on the other side. So if self is none, we do this. Else, if it's equal to value, do this. If it's left, so since we can handle what. node doesn't have a value yet, just use the given value. Oh. I think it's checking the right side and not the left. Sorry, it's checking the left and not the right side. So say there's a value less than, so you see the 6 should be going to the other one. Update your insert, bro. If volume the given value is less than the nodes. It don't fuck me up, it's just and. I can just do I don't know if you guys understand why I messed up. I didn't even understand. I don't care about this indentation they told me. When I saw that the instructions say if the given value is less than a node and the node doesn't have a left, then you do that. That's why I put it all in the same line. I guess you could just do if this and then you do if this is none, then you do this. I don't understand why you can't just put and. But let's check the solution real quick. If not self.val, same shit. Self.val return. Boom. If self, well, the thing is, I don't need to just return this. I can just put it all at the end and just put return self. If self.val is equals val return. Okay, so if the val is less than, if self.left. Thing is like saying this is way more clear because it's just like no. If self.val, is that true or no? I see what they did right there. I kind of like it. Might use that in the future. So if that's none, which it is none, we're gonna insert Alright, let's try to understand this code. I would like you to explain this code so I understand completely what is going on, and please do a visualization. Example so I see how it works. We got next this and that. Based on the user ID, because comparison is less than armed in the user class, we can just compare entire user objects directly. So if the current node is empty, if valid now, we store the user here and stop. This user happens at the very beginning when the tree is just created. If the value is equal to the current node, we do nothing. We don't allow duplicates. That's why that's weird. Okay, I see that's okay. So if it's equal, I thought I don't know. I didn't realize what that was for, but I realize now. I just did the step what they asked, but if the value is equal to the current node, then we just cancel, because it's there's no way that you can have duplicates in a binary search tree. If the value is smaller than the current node, we go left. If there is no child, we place it there. If there is a left child, we just recursively call insert on that child. I see. If the value is greater than the current node, we go to the right. If there's same logic, I'm not even gonna look at it, same logic. If there is no left, if there's no, how do you say it? Yeah, if there's no right child, we insert it there. We make that left child, like we place it there, right? We place it there. And for the right side, say there's no right side, we place it there. If not, we recursively insert it there. Yeah, on that child that's already there. And I remember this. You can't in binary search tree, a parent, wait, it can't have two something. I forgot. Something about two. You can't have two children. Each node has a value, may have a list of children. Wait, what is it? Just let it say. I swear it says something about two. You can't have more than two. A left child must be listed as hers. Wait, instead of an unbounded children, each node has two children, at most two children. That's what I'm saying. So that's why you see if it's like one or two, like where are we? Alright, the next thing is here, right? So insert review. Inserting into a binary search tree, like most of its operations, is very fast. Are we inserting insert review? So okay, yeah, let's do the insert review, and then I'm gonna stop here. Oh, it's almost an hour. Cool. I'm gonna go work on my personal project, and then I'm gonna come back to this tomorrow. Today's Thursday. Goal is to finish this section by Sunday night. So I have binary trees done, and then we can move on to red black trees, whatever the fuck these are. But yeah, we gotta put a dent in this already, because I really want to finish this already so I can start decoding crazy. Okay, let's finish this insert, and then I'm gonna end it. Insert review. Inserting into a binary search tree, like most of its operations, is very fast. Picture the algorithm you just wrote in your head. How many comparisons does it take to find the right spot for a node? It requires one comparison for, yeah, so you're just gonna have to, yeah, one comparison. You just have to compare it from the levels as seen in the picture. Like, so we insert another one, we just have to compare it to like the parent. Like, say this one has one, you go here, then you go. I see how binary search trees work. It's pretty simple. It's pretty simple. You only for each level of tree making. Honestly, I had a harder time with linked list. Not sure why, but after understanding linked list, I see how the nodes shits work. Like, it's so much faster than just a list, because you go to the node and then you insert the node. When you want to, yeah, like you're saying, insert review. So we're talking about inserting. When say we want to insert something, first thing we check is the parent one. If it's greater than or less than, remember, greater than goes to the right, less than goes to the left. Boom, done. Now if we go to, say it's greater than, say 20. So 20, we gotta have oh, by the way, when we insert another factor with a BSF, I like talking because it helps me understand. Another thing we gotta know is that duplicates matter in binary search trees. If like we did just in the code right now, if the value is if it's the same as any of the nodes before, cancel and just return it, because it can't have any more. Does that make sense? Another thing, okay, so boom, say it's not a duplicate, then boom, we check if it's left to right. Honestly, why? Okay, so obviously you have to, if it's empty, you make this the self.val equal to val. Boom, boom, that's done. So then you check if it's a duplicate, because if it's the same as that, then you just cancel. Boom. Then the next thing you do is remember, left to right, go to the right, check if the child. If this child already has 2, you move to the next child. So let's say this child has 2 already, then you move to the next one, and then boom, this has 2. And then if you want to insert to the right side, it should be this one right here. Left, right here, it should be right here. You insert. So yeah, what is the average big O column of dot insert? Wait, let's see. It's O log n, right? Yeah. Order login is very fast, practically as good as O1. The most cases of the tree has a million nodes. We only need to make 20 comparisons to find the right spot for a new node. If our tree is 2 times larger than nodes, we'll need to make 1 more comparison per insert. 21 total. Yeah, I'm starting to understand this. It's clicking with me why data structures is important. It's just all about speed. Yeah. But alright guys, I count this as a W day because I understand what's going on. And yeah, so whoever's watching this, I appreciate you for watching. It means a lot to me. Yeah, so that was today's video. I'm gonna do some personal stuff right now, so yeah, I gotta end video. I can't just jump back to this. So yeah guys, alright, see you guys tomorrow. Later.